Hey robot makers, hope you're having a good day so far. So do you want to know how to create your own DIY Lego compatible blocks using Fusion 360? Then this is the show for you, so let's dive straight in. My name's Kevin, come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, yes, so this is all about how to create in Fusion 360 robot parts and how to use one single model to create loads of different types of block. This is really, really cool. I had so much fun with this. And as you can see from the table that I was just showing in the pre-show, I've created quite a few little components like the rangefinder. I've created one for Raspberry Pi Pico holder. And I've also got a little N20 motor holder as well in a standard kind of block. So you can see the little motors in there as well. So the design goals for this session then, we're going to have a look at the anatomy of a block, a generic compatible building block. No copyright infringements, please. We're going to look at the different types of block that there are. There's a couple on the screen there. We're also going to look at some key measurements so you can build your own. I've got mine printed out just here, just so I get them absolutely correct. And we'll do a Fusion 360 demo, of course, as well to do this. Okay, so let's have a look at the anatomy of a block. So first thing is, blocks have studs on them. This is one of the key measurements in the building block, and we often describe the block that we're looking for by the number of studs that are on it. So you might say the one that's on the screen at the moment here, just find that, that could be described as a 2x4 because it's got 2 studs wide by 4 studs long. And there's lots of other variations on that as well, 2x3, a 1, a 1er, that kind of thing. So studs are a key part of the anatomy of a block. The pitch between the studs is very, very important. That means that we can create compatible blocks with other building systems. And underneath the block there is these columns. If I just grab a block from on the desk here, this is a genuine Lego brick. You can see that that's got a number of columns underneath it. It's got 3 columns and it's got that little separator. It also has those little pieces that help grip the studs as well. So one of the things I found while I was doing the 3D printing was I've got 2 3D printers sort of left and right of me. They all print differently, so you will have to adjust your tolerances ever so slightly on things like the studs and on underneath where the columns are, just the width of them, just to make a really good fit for your particular printer and for your particular filament that you're using as well. So these definitely aren't as good as genuine Lego bricks, but they're certainly compatible, and if you sandwich them between genuine Lego bricks, they work just fine, I've found. Okay, so yes, studs. So a standard stud on a Lego brick is 1.8 millimeters tall. So we can check that with our calipers. We can put the little thing down there and measure it, and we get 1.8 on the measurement there. And the pitch between the center of the studs is 8 in both directions. So where we have our little stud blocks between them in all directions, the pitch between them is 8 millimeters. And the diameter of a stud is 4.8 millimeters as well. Just checking my notes to make sure, absolutely sure that's correct. So there's some of the key measurements that we need to remember when we're putting this together in our design software. So standard units. So one of the things that you might be familiar with if you've been playing with Lego as long as I have is there's a standard height of the sort of one tile piece, the tile piece, or the plate piece. They are described as 1 unit high, and the larger block, this one here, is essentially 3 of those standard units high, and it's again the same distance square. So we can describe these blocks as being either 3 single plates high or just 1 larger unit high. So I'm calling this a standard height, and it's 3.2 millimeters for a standard height, and therefore 9.6 millimeters for a larger standard height. So we can describe these blocks as like a 4x2, and it's 3 lower standard heights high. Okay, so let's go on to the next slide. So that you do need to have a tolerance between these bricks. This is something that if you don't include, you'll find that the bricks, when you try and put them together in a pyramid kind of shape like that, let me just grab a couple of blocks here. So if I get 3 blocks and I just try and stack these together, the reason those bottom 2 pieces can sit side by side is there is a very slight tolerance. It's 0.1 of a millimeter on each side. So we need to make sure when we're designing our Lego block, we we define the length as being the number of studs, so say it's 4 studs wide, by the pitch, and then we have to take off that the tolerance to make sure that they fit side by side. We need to do that in both directions, length and width, but not height. That seems to be okay. So yes, the length of a block is the number of studs times the pitch. So if we have 4, that will be 4 times the pitch, 4 times 8, 32, and then we have to take off that the tolerance, which is 0.2. You can see the tolerance described at the bottom there. And that will allow them to sit nicely side by side. So the columns underneath, they are there to provide a bit of extra rigidity and strength, particularly when you're crunching these things together. It just gives them that extra, keeps all the studs nice and tightly together. So the number of columns in a block can be described as the length number of studs. So if this is 4 wide, it's 4 minus 1, so it's the length minus 1. And if this is 2 wide, then you can see there is only 1 column deep, so we need to do width minus 1 as well. So that'll be quite important when we're designing out our parametric Lego blocks, Lego compatible blocks in a minute. So types of elements. So one model can actually define all these different types and more blocks. This is what's really cool about using something like Fusion 360 and using variables parameters within it. So we can define blocks, which is this yellow one, the plates, which is the green one on the bottom there, and tiles, which is the one on the right hand side, the grey one. And the difference between them is just the height for the plates and the bricks, and the tiles are smooth. So the idea is they're kind of a finishing piece, and you tend to put them on top to give things a nice kind of look to them. And we can create all of those different types of block just using one model. So the key measurements that we need to remember, and if you want to screen grab this, print it out yourself, you can do. I've got my copy of this as well to hand, just so that I can refer back to it while we're building out the model. And in Fusion 360, you can see there's an FX button, which is on the standard home ribbon. And when we press that, it brings up the parameters table, and we can add in there our own custom parameters. And that's what we'll be doing at the very beginning of our modeling session. So you can see there we've defined the length and the width in studs. They're not any particular type of unit, so make sure we don't include like millimeters or inches on there. This is no units because we're just going to say it's 4 long by 2 wide. The height is in millimeters, so it's going to be low times 1, which will make it a plate or a tile. And we can see low there is 3.2 millimeters, or the high one is 9.6, and that's the difference between the small pieces and the larger pieces. The stud diameter is 4.8 millimeters. The stud height is 1.8 millimeters, and the spacing, that's the distance between the center of the stud and the edge of the block, and that's the same in both directions. We'll see that in a minute, but that's what the spacing is for. The pitch is 8 millimeters. The tolerance is, as we've said, is 0.2. The shell, and we'll have a look at what the shell is very shortly, but essentially it makes something solid. If I can get this just angled right, you can see this has got like an inside to it. That's what shelling does. It will sort of carve out the inside to a particular width and depth, and that's what the shell is. So 1.6 we've got there. Just making sure I've got that right, yep. And we have the columns as well. So them 3 columns that we saw on that 4x2 block. There's an inner and outer diameter that we need to get, so that we get the thickness, which is like 0.85 millimeters. And then there is a spacing between the center of the column and the edge, top and bottom, top and left as well. So they're the key measurements. If you want to screen grab them, you can do. You can probably find them online as well. So if you like what I do and you want to help support the show, you can all go over to Buy Me a Coffee, and we've had quite a few people buy a coffee, which really, really appreciate every single person who does that. It really does help out pay for the equipment, the software, all the streaming services I have to use just to provide a show like this. Some people think that YouTubers are rich and stuff, but when you've got a very small channel, you're a long way from that, believe me. So if you want to help out, you can either buy me a coffee or you can join the YouTube membership, which is just on the YouTube thing. Next to the subscribe button, there's a join button as well. And I do go live every single Sunday at 7 o'clock Greenwich Mean Time, so you can find me on YouTube, Twitch, Twitter and Facebook as well. Okay, so you can also like, comment and subscribe to this video as well on any of the platforms that you're watching on, and that again helps the algorithm just show this to other people who are like you, really enjoy this content. Okay, let's get back to it. So if you want to join me on Discord as well, we do have a Discord server. Some people wanted to have a more deeper conversation, so you can join me on Discord as well. Go to action.smarsfan.com/join-discord, and you can see everyone on there. And the first 100 members will get a special founding member badge role as well. Okay, let's get over to the demo, shall we? Let me bring up Fusion 360. Let me just get myself sorted down here. So there's Fusion. Let me just move that out of the way. And let's get to it. So there we go. Right, so I've got Fusion 360 open. The first thing we need to do is just save our project file and give it a name. So I'm going to call this one blocks. Okay. So the first thing we need to do is create a sketch, and we want to create that sketch on this this sort of bottom, the top plane. Is it the Z plane? And what we want to do is we want to create a rectangle. So I'm going to go over here to the rectangle tool. I'm going to change it to a center rectangle, and then I'm going to find the origin point, and we're just going to pull that out from there. So the first thing we need to do is define some of our parameters. Remember, in that that list, we're going to add a couple of parameters in now, and we'll build these as we go, so you can see why they're there. So what we're going to do is we're going to come over here, we're going to create a user parameter, and we're going to set the units to no units, and we're going to call this one length. And let's start off with a nice standard block 4x2. So that's the length, and then we're going to go for the width. That also needs to be no units, and we're going to make that one 2. And we'll also define, while we're here, the tolerance and the pitch. So if you remember, the pitch was 8 millimeters, and the tolerance is 0.2. So that's 0.2 millimeters as well. Okay. So let's now press D for dimension, click on that line there, and we're going to make that to be that formula that we had before, which was the length times the pitch, but we also need to add in the tolerance. So I'm going to put them in brackets, and then I'm going to say minus tolerance. So now we've got 31.8, because it's 8, the pitch is 8, it's 4 blocks wide, 4 times 8, 32 minus that 0.2 tolerance, and because we've centered this on the origin, it takes the tolerance away from both sides sort of equally. Okay, so that's the length. We now need to do the same with the width, so we can now say the width, and I've just pressed W, and it's also brought up just as a auto complete there, the width, so I can click on that, and I can then say width minus pitch, sorry, not width times pitch, and then I can put that in brackets, and again just minus off the tolerance from there. There we go, 15.8. So that's the first thing that we need to create. So let's click finish on there, and we now want to define what the height is. So let's go back to our change parameters and add in some extra parameters. So we're now going to say, let's start off with something called low, and that's going to be 3.2 millimeters. That's the height of a tile or a plate. And let's also define high as well, which can be the, it's essentially the low times by 3, because it's 3 times the low. And then that calculates that to be 9.6, and we know that's our high value. And I think that should be good for now. So let's now do Q to extrude this, and we're going to extrude that by, let's do it by the height, by the high. There we go. So it's looking a little bit like a Lego block now. In fact, let's press A for appearance, and I'm going to throw on there a nice red colour. So I'm just going to search in the library for red matte, and I've got plastic red matte. Oops, I'm going to throw that on there. I don't know why that jumped away when I dragged and dropped. There we go, and we can just click OK, close that out. Okay, I'm just going to save that as well. Save as we go. So now we need to define the studs. So we're going to create another sketch on the top of the block. So let's come up to that top surface there, and then we're going to zoom in a little bit. And I'm going to create a circle. So C for circle. It doesn't matter where we put it to begin with. I'm then going to press D for dimension. And before we do D for dimension, I'm going to change the parameters. I'm going to add in the 3 stud parameters that we need. So the first thing is the stud diameter, and that is 4.8. We're then going to add in the stud height. Stud height and that is 1.8. And then the final stud one is stud and spacing, I think I call this one, and that is 3.9 millimeters. Okay, so let's close that. D for dimension, let's just grab that and change that to be the stud diameter, like so. And then I'm going to click on the very center point of that circle and then the left edge. I'm going to drag that up, change that to be stud spacing, and then I'm going to do the same thing again. I'm going to click on the top surface this time and then the center point and then drag that out to the left, and that's also going to be the same stud spacing. Okay, that's all we need to do for that sketch. And now we can click in the middle there, we can press Q to push and pull, and we're going to define the stud height there as the height that we want to extrude it by, which is that 1.8. Okay, so we've got one stud. So this is where the parametric thing starts to get really clever. So we're going to do a rectangular pattern to define what that is. So let me just drag this rectangular pattern out here so you can see what's going on. So the first thing we need to define is features. So the type is features, and along the bottom, if I just hide that buy me a coffee thing for a second, you can see we've got this little timeline of things that we've done. So I'm going to either select the feature there, or if I didn't want to select it there, if I just cancel that out, I can actually just click on the model and it figures out that that stud feature that we've just created, that we've extruded up, that's the thing that we want to have a rectangular pattern of. Next we need to do the directions, so click on select and I'm going to select that edge and that edge there, so the top and the left edge. I'm then going to say that the type of distance is going to be spacing, because we're going to define it via the pitch. So the length is going, so the quantity is going to be the length. So if I just type in, I'm making a mess of this, length in there. And then the distance is going to be the pitch. So I press that, you can now see that's looking good. And if I do for the quantity in the other direction is going to be width, and again the distance is going to be the pitch. We have a Lego block. And we've used variables, so if we go back and change those variables, it will change all the dimensions of the block. So it's really, really cool. So that's the top surface. Let's now flip this over and then start looking underneath to them columns. So we're going to click on that bottom surface there. We're going to go to our change parameters and add in a couple of extra things. So let's go in here and add in shell. Our shell is going to be 1.6 millimeters. Let's add in a columns one as well. So we have column, I'm doing this in lowercase now, it doesn't really matter what case you do, column inner, and that's I think that's 4.8. And then we're going to have another one which is column outer, and that's going to be 6.5. And then we're going to have the column spacing, and that's going to be 7.9. I think that's all good. Right, let's click OK. So I've selected that bottom surface. I'm going to click on this shell command, and then I'm just going to type in shell, which is that parameter that we've just defined, and then click OK. Now you can see what's happened there. It's created, it's kind of carved out, but it's also carved out, because we've got these little studs on the top, it's carved out those as well, so you get that interesting effect. And that's what you also get in a genuine Lego block. When I look in there, I can see the same thing in there. I don't know if I can show that on the camera, but you also get that same effect in there as if that's what they've done, these little things. And they've also got the columns in there. So let's define the columns. So the interesting thing about the columns is we want to be able to make the height of this block a parameter. So we need to be really careful about how we choose the next thing. So we're going to do another sketch, but we're going to select that bottom face. So that's the most important step there. We're then going to define two circles. So press C for circle. I'm just going to drag out that. I'm going to click in the center again of that one, and that will make it so it's concentric circles. And I'll pull that one slightly larger. I'm going to do D for dimension. I'm going to click that inner one, drag that out, and then type in column, and then select column inner. Click on the other one, drag that out, column outer. And what we're going to do now is we're going to just click that center point on the left. I'm just going to drag that up, and that's going to be the column spacing. like so, and then I'm going to click the center point and then the top edge, drag that to the left, and that's also going to be our column spacing. And if we've got that right, that should look pretty centered between those 4 points, and it looks pretty spot on to me. So I'm going to finish that sketch. Now that sketch is kind of floating at the moment in space, so what we want to actually do is press Q for push pull. I'm going to select that profile that's in there, and then I'm going to push it up slightly, and then in the extent type I'm going to select to object and select that inner face there, and that will extrude it up inside the block from the bottom surface. So that's okay for one. So we're going to use that same trick that we did before with the rectangular pattern. So it's still on features, which is good. I'm going to select that column that we've just created as the object. The direction again is going to be one edge, like a top and a left edge. We've set that to spacing, which is okay, the distance type. And then the quantity, let's try just typing in the length. The pitch is the distance. And then the quantity is going to be the width. And then we're going to have distance as well. So the distance is going to be the pitch as well. Now you can see there, that doesn't look right. We've got too many going on. So let's go double click on that. And then where we've got length, let's just do length -1. And that's what I was mentioning in these slides earlier. We just need to do whatever the pitch is, so not the pitch, the width is -1. Like so. And there we go. That's our completed first model of our Lego block. So you can see there, that looks nice. Okay, let's play with this because this is now parametric. So we go back into our parameters and we change this to be 3x2 instead. Let's click OK. Look what's happened. We've now got a 3x2. Let's change this to be, I don't know, a 4x8. But we'll change the height to be, let's have a look. Let's change that where we've got high. Let's change that to just be low times 1. Click OK. Look what we've got now. We've got another, I've got a plate. And if we flip that over, we can see we've got all the features that we'd expect to see on the plate as well. Now what will happen if we make this 1 by 1? We're gonna introduce a bit of a problem here. So let's go by 1 by 1. And let's see what happens. We get this weird quirk where we still get that column appearing. So what we can do to prevent that from happening is simply come over to this in the timeline at the bottom of the screen, right click, and we can say suppress features, and it just turns off that feature that we've created. So we've now got our block, which is our one singular, one high block. And if we want to go back in there, we can turn that back on just by unsuppressing the feature, and then we can do other things as well. So let's make this one, I don't know, 10 by 7. That's not a real Lego brick, is it? Let's go and change the height, the low to be, let's make that one 6. So it's going to be like the double height. Let's click OK as it's just calculating that and drawing all those studs out. There we go. So that's a block you would never see in the genuine canon Lego. But there it is. That's what it would look like. So you can see you can do all kinds of things from this. So let's just put this back down to be, I don't know, the 4x2. And let's change that to be just 3 again. Okay, so that's our regular kind of Lego block. And if we just change that height again back down to 1, so it's a plate, we can click OK. There we go. We can flip that over and see that we've got the 3 columns there as well. Now, if we want to make this a tile, can you guess how we do this? We've already kind of done this before. So if we go over to that block, we right click and we suppress the feature, we've now got a tile. So we've looked at a tile, we've looked at a plate, we've looked at a block, a super block. We can do all the things. We can do all the things with this. This is what is so cool about it. So we can right click on there and unsuppress features, and then we've got our block back. So let's go back in there, change that height to be 3 again. And we can change, let's have a look, change that to be 1 by 1. I know, let's make that 3 high, by 6 high. So then we get like a tall piece there, and we can suppress that column so that we don't get that weird feature appearing. That looks like, remember the window pieces? There's like little window shutters, that's what they look like. So you can have so much fun with this. And if you've created one, you can just go into your bodies, you can save that out using the save as mesh, save it as an STL file, and then you can throw that in your slicing software like Cura and 3D print stuff. So that's what I've done. So I've created regular kind of block. I've got these N20 motors. Let me just go full screen for a second. We'll come back to this and we can show you how we do these. So these N20 motors are really great. These are the kind of motors that are in the Trilobot that we looked at last week. So this thing is powered by a couple of those N20 motors. I think they're the 110 RPM. And we can fit one of these quite nicely inside a Lego block. I was looking at them thinking, yep, that looks like it will fit quite nicely in a regular sized Lego block. So I've taken one and I've punched out a hole and I've made it just the right height that we can sit another Lego block. So if I just get one of these plates, for example, push that on there, we can now hold that motor in place quite simply. And then on the newer version, which I'll show you on Fusion 360, I've created some cutouts so that we can get the wires in and out. I've actually got them on both sides as well, so that the wire coming from the motor has got somewhere to go. Another one that I've created, which is for the rangefinder. I thought this one would be really useful. So that's a standard rangefinder, and it's kind of 6 by about 2 high. And there's a couple of different ways these pins, some of them come straight out, some of them go straight down. And that simply just slides in, so it's as easy as that. So this has got some extra little features in that it's got a cutout either side because this is slightly wider, and it's also got those two holes for the rangefinder to slide up. Looks like a piece of Duplo to me, that. And then finally the other one I created was a Pico holder. So this is looks like a regular kind of plate. It's white, so it's not showing up very well on this camera. And it's got some little nodules on there which are perfectly aligned so that we can put our Pico in place there, and it'll sit nicely and firmly on there. And it's also got some slots for the headers as well. So if we get grab some header pins just on my desk here, we plug some of these in. We've got plenty of space for that too. There we go. So you can see that our header pins can fit nicely through there, and we can make our Lego be powered by a Pico. Okay, so let's have a look how we can do some of these. We've got quite a bit of time. I didn't realise it'd be quite as quick to do this, but there's so many things you can do with this. Right, let's go back to Fusion. So I'm going to open up some of the models that I've been working on. So if I go to, let's have a look, the rangefinder, and I'll show you how we built the rangefinder piece. Okay, so this starts out just like the regular block that we just created does. So there is a sketch. Let's just define the sketch. There we go. And open up the sketches. And this uses the same parameters that we've typed in previously, so you can see there, might just be a slightly different case. Some of them are not uppercase like we did before, but it's all the same measurements. So we then extrude that up. And what I did is I just took a guess to see how many blocks it needed to be and then worked with it. So that's just a solid block. We then create the sketch for the studs on the top, just like we've done before. We extrude those up. We do the rectangular pattern. These are all parametric, so if I get it wrong we can adjust it. We've shelled out the bottom like we did before, so if I flip that over, we've got that. Now I don't include on this one the columns because we need somewhere for the rangefinder to slot into, so the columns wouldn't work on this. So the next thing I've done, I did define the columns, but I didn't actually extrude them out. So the next thing I did was, in fact, I did fully create them, I just suppressed them. In fact, if I unsuppress them, there they are. So let's suppress that again. And the next thing I did, I brought in the rangefinder itself. I've got a 3D model of a rangefinder. And I was looking to see how is that going to fit in there. Is there enough width, or do I need to make it like an extra block wide? So I then capture the position, which is what that command does there, made it nice and centralized. And then I create another sketch. The sketch is for the rangefinder, what do you call them, like the goggles at the front. So I discovered they're about 16 millimeters in diameter. If I get my calipers and just measure one of those, just measure how wide that is, it's about 15.8 thereabouts. So 16 millimeters would be just about enough tolerance around the edge. And I thought, well, if I give it 17, then it's got plenty. It's got plenty of between them, just in case when they manufacture they're ever slightly apart. And then I made sure that they were about 11.15 millimeters from the center. That's the distance between the center point of the rangefinder and the edge of the model. And then you can see it's 12.2 from the center point to the top of the model, and that seemed to be just about right. So that means we can then punch out, which is the next one. I just need to finish that sketch. So the next one, if I just pull that forward, we just spin that around so we can see it. You can see now that it's punched out the hole for the rangefinders. The next thing we needed to do is just define another sketch in there, which is for, if we look on the very top there, and I just enable that, you can see on the edge there, there's ever so slightly a little rectangular block. And that's going to allow us to cut out the side, because it's slightly wider than the shell, and I didn't want to change the shell because that's part of our structure. And we then just extrude that down, cut it out. So that's done it on one side. We need to mirror that on the other side. So if I just hide this rangefinder for a second, you can see it's only on one side that it's actually cut out at the moment. What we want to do is mirror that. So we can use the mirror command and mirror it over to the other side. So it's quite straightforward to use the mirror command if you've never done that before. You simply just select the feature you want to mirror. You select the mirror plane, which just happens to be our origin point. If I just move this round there, that's our origin plane there. We can just mirror it round that. And then it cuts it out the other side too. And that's pretty much it. I think I just captured the position then of the rangefinder so that it's nicely positioned. So you can see if we click on the bottom there, it's nicely positioned inside. And if we look at the front side of it there, it's nicely in place. And the bottom of the rangefinder is flush with the bottom of the piece. And if we look at this piece on the camera as well, we can see that it's nice and flush. It doesn't protrude out. So now Polly would need to ever so slightly adjust this, because if we want to plug this in place here, we can actually plug it in place. That doesn't seem to be an issue. It just happens to be a fluke that that fits there because I didn't allow enough space for the studs to fit there. But we can see that will fit nicely on a couple of pieces. In fact, if I just put them together, I'm just constructing a piece of Lego there. Let's just do that. It does actually stay in place quite well. There we go. So that will sit in the front of our robot, and it can sense distances. And it's quite robust. It doesn't seem to move around or anything. We can plug our cables in there as well. So we'll probably just need to allow a bit of space there to do that. So that's the first block that I did. And then I was thinking about what else can I create. So I then looked at the N20 motors. So let's pull out the N20 motor block. I did print two of these. I didn't quite get the height right. So you could put a motor in, but then you couldn't actually put it on because there wasn't enough distance for the studs to sort of come into the bottom piece. So let's just close out this. And let me flip this over so you can see what's going on. So I've got another model of an N20. So that means we can just have a look and see, does this fit in? So the first thing I did on this one was, again, just to model out a standard block. So if I go all the way back to about here on the timeline, you can see this looks like a standard block that we've just been defining. Now the height of this is a little bit higher than your regular ones. So if I go to the height, it's 5 standard units high rather than 3. So it's got 2 extra bits to it. And we then create, I bring in the motor. So if we flip this round to this side, we can see that the spindle is sort of sticking through the block. We haven't got a hole there. So I do this because I can then create a sketch. Let's see what happens on here. So that's the I think this is just the bit that we don't use for the columns. I define them all the time just on there. And then what have we got there? Not sure what that is doing. Oh, these are the steps for the motor, I think. Right, so yeah, this is what I was looking for. So I then define a sketch on the front. I can see where the spindle is coming through. That's 3 millimeters. So I've used the outline offset tool. So I've got 3 millimeters, offset it by 0.5 millimeter. So it's like 3.5 millimeters round. And then we can push that back to extrude it through the brick. So the next command will push that back, extrude it through the brick, and we've now got somewhere for that to go. Right, so that piece, I've just realised what was going on there, that sketch that's inside. Let's flip this over and show you what's going on there. So I want to be able to hold this motor in place, otherwise it will flip out a little bit, it'll be a bit wobbly. So what we can do is we can define a tiny little piece of plastic, like a little nub, that will stick out and enable the motor to sort of sit into place and push up against this little nub. This is what happens in SMARS robots. If you look on the bottom plate of a SMARS chassis, you'll see these two little plates, two little nubs that the motors are flush against. So the way that we can see this, if we go into Inspect and Section Analysis, we select that face there and we just push through, and then we click OK. We can see inside now the model. If I flip that round, can you see this little piece of plastic that's just, oops, a bit too far in there, just here? This piece here is allowing that motor to sit up against that nice and flush. So that's what those sketches were about there. So there's a sketch that just defines it, we pull it up, and then we just chop off the back of it there with a chamfer. Okay, let me just turn off that section analysis. Let's get back to our regular view of the block. And you can see there that I've also now started to create a little cutout for the wires to come through. So that's essentially what the next couple of things are about. Just cutting out the hole for that. So there we go, we've got some little cutouts either side. And I did also bring in here a little 2x2 plate so I can just see, does that fit nicely? I can do that section analysis as well, so we can see that that's fitting nicely in there and that the motor's got a bit of distance between it. Oops, Fusion sometimes does this on a Mac. It sort of sticks and then you have to save the file or close it. So you can see that the motor's nice and flush against the very top, and there's a bit of distance between where the studs can come in now. And I found that it wasn't quite enough when we printed it out. So if I grab this one that's the good version and then the one that's the bad version. So if I push this into place, that's it in place there. You can see that it's sort of staying up in place because of that little plastic nub. But if I try and get a plate in there, there isn't enough distance for the studs to be able to push into place. So I printed out a slightly larger version. There's one extra unit. Let's put that in place there. I can now get the plate, put that on place there, and then we can put a plate over that. That keeps the motor nicely in place. And the wires can come out either the back or on the newer version of the model, which I've got here, or the side, either side. Cool. So they're the pieces that I've created so far. The last one, so if I just close this one out, is the Raspberry Pi Pico holder. So let's just find that one. Okay. So I've got a question there from Dale about what stops the motor from falling down, and that's that little piece of plastic that I've just described, that nub. The motor will come up against that, and the pressure of against the nub actually holds it in place, so it stops it from just falling out the bottom. Just show you that again. So if I just go full screen, show you this. So there's the bottom section. Inside there's a little nub that when you push this inside and push it up against it, it will hold it in place. As you can see there, it's sort of held in place. Okay, let's go back to here. So I thought this one, we could start off with like a regular plate, 6x10 I think that is, which is a standard plate in Lego. And I then brought in a model that I created a while ago. Let's see if I've got it to hand. There it is. So I created this model, which is for a Raspberry Pi Pico, and it's essentially just like a zero case, but for a Pico. And the Pico sits nicely in there. The little standoffs, the little nubs that are in there, hold it in place nicely. Let's see if I can get this out to show you what I mean. I'll just pull that out so we can get that out there. So in the bottom of this design, we have some little standoffs, and they protrude ever so slightly, and they're designed to be exactly the distance for these 4 holes in the Pico. So if I put this Pico into there, let's make sure I get this right. There we go. It's a bit of a tight fit for the there we go. That's fitting nicely there. So now that's in there and that's not going anywhere. That's really held in by those little 4 lugs, and we've got the power there as well. So I wanted to use that exact same model in Fusion. So I brought in the same thing. I brought in the actual Pico itself as a design. I've got that. Let's just bring that in. There we go. And this is the exact model that I created before. It's even got like a top, and then we do have one where it is just, excuse me, it's the bodies. There we go. So there we go. So I can get the exact dimensions we need to push those little nub things through the holes in the Pico and hold it into place. I needed to include some areas where the headers can be. So if we've got headers soldered on, we can have them come through the bottom. And when I did the shell command, it also shelled out the bottom of this as well, which is quite nice. It uses less plastic. Though when you print it out, obviously it does need to use some kind of support as well. Okay, so we can quickly go through how this is created. If I go back to, let's close that out, click on the holder. So we can see, we start out with a regular sketch. Let's just enable the sketches so we can see what's going on there. So it's just like a regular plate that we extrude out. I extruded out first of all the place where I wanted the Pico to sit on. I extruded out a little sketch for the little nubs that go through the bottom there, and then we have a bit of a chamfer just on the edge of the nubs so that they're rounded. I then create some more extrusions, so I extruded out from that very first sketch the rest of it. So if I just take off the Pico, you can see what's going on here. So it's just like that at this point. I then extrude up, if I can just grab that there, it's just not letting me do it, there we go. A single stud. I then use our pattern. Now what I've done on this pattern, if I just double click on here, there's this button called suppress, and if you click on suppress, you can select individual features that have been replicated and turn them on and off. So all I've done here is I've replicated the entire grid, and then I've just painstakingly clicked all the way around that feature so that that's where we can have the cutout. So that's what we can use for that. We use the suppress feature. So there we go. So that means that we've got a very specific pattern that we want. I then shell out the bottom. I think I create the, if I just flip that over, I create one of the columns. We then do the rectangular pattern. Again, we use the suppress feature on that. So if I just click in there, click on the suppress, you can see I've unselected all the middle ones so that we don't have them sort of floating in space or anything. And that means that we get just the pattern that we're after. And then the last things that I do, I think if I just drag this forward, is I cut out some holes for the headers. And I think to begin with, was that, I think I actually cut out a slightly larger one on the next one. There we go, just make it just wide enough. There we go. So I found this was quite a nice thing to be able to print out. I'm really pleased with how this has turned out. The only thing I found with this particular plate is because there's support material that's being printed, and then the bottom of the plate is kind of a bit messy. So there's a little bit of cleanup work. If I show you on here, let's go full screen, and I can show you on here what I mean. There's quite a bit of mess on there that I would have to clean up, and that currently that's preventing like a regular Lego brick from sort of pushing into it, and that's because there's bits of plastic protruding down and it needs to be really clean on there. So that's the only thing about printing out the plates. You're not going to get as clean a piece as like a genuine piece of Lego, but you can plug, you can attach things to it, and it's fine, it's compatible. But I found with my white PLA on the Ender Pro 2, whatever it's printing, it doesn't seem to print the studs well enough. They're the right dimension, but when I put them on there, they don't sort of hold on, they will fall off. And that's because the tolerance is ever so slightly out. But it does let you put them on into place. It's the right pitch and everything. You can see there that's a perfect fit. It's just not quite on there. And that's more to do with the PLA and the 3D printer than the actual model that we've designed. So I hope you enjoyed that, how to create your own Lego compatible modules in Fusion 360. It's really easy to do. It's really fun to do with Parametrics because you can design a whole host of bricks just by playing around with some parameters. And then once you've done that, you can then base that, you can base other models on that piece, such as our rangefinder, our little motor, and also our Raspberry Pi Pico. So I'm intending to do more of these things, so I can build an entire robot with a couple of motors on there that can it can move around, powered by a Raspberry Pi Pico. So watch this space for that. When I've got some time, I'll put that together and we can make a Lego Smars. That's on my plan, my to-do list. So if you're watching on YouTube on replay, this is the point in the video where I'll say bye for now. And people who are watching live can join the QA after this, and we'll have a look at some of the questions.